Chapter 7, we're interested in geometry, so we're going to look at section 7.1, where we're going to look at angle measures and number of sides. So, basic polygon properties. So for everyday purposes, we know that a closed polygon has a distinct inside and outside, and any 2 points on the interior can be connected by a simple line. So, for example, squares rectangle, pentagon are all relatively straightforward. You notice, though, that what we're going to be particularly concerned with is the idea of a regular polygon. A regular polygon has all sides of equal length and all interior angles of the same measure. So we notice that a square is a regular polygon, but a rectangle isn't unless it's a square. A pentagon can be a regular polygon, but it winds up being very specific. So we actually notice that if we look at a square is convenient. For a square, we know that it has 4 sides and the interior angles measure 90 degrees. So that's relatively straightforward. We can see that those interior angles are all right angles, they're all 90 degrees. The trouble is, how do we find out the measure of the interior angle for a pentagon? So we'll pretend that this pentagon is a regular pentagon. What are the angle measures for a pentagon. So here we can actually be clever. We notice that if we break that pentagon into 5 triangles, we notice that those 5 triangles at the center have to make up a complete circle. We can break it into 5 triangles that together must account for 360 degrees at the center. But that means any one triangle must have one angle that is 360 degrees divided by 5, which gives us 112 degrees. No, it doesn't. 360 divided by 5 is 72. degrees. And so that means that we've got these 5 triangles that all look like 72 degrees, and they're all going to be isosceles. And so we notice that we can take 180 minus 72 is equal to 108. And then we know those other 2 angles have to be 108 divided by 2 is 54. But then we notice that we put everything back together again. The triangles are going to be 72 degrees by 54 degrees by 54 degrees for their 3 angle measures. But then we go back to our pentagon. We notice that those interior angles are going to have to be 108 degrees. So we actually notice that this is kind of the hard way. We actually have an easier way to do it. We notice that in this case, we notice the sum. So the interior angles for the pentagon are each regular pentagon are each 108 degrees. So how can we do this more easily? It turns out that the sum of the interior angles for any polygon so the sum of the interior angles for any closed polygon with n the sides must be n minus 2 times 180 degrees. And so what that means is that for a regular polygon, with n sides, the interior angles must have measure n minus 2 times 180 divided by n. And so we can verify that for ourselves. We notice that for the square, we're saying n equals 4. We get 4 minus 2 times 180 divided by 4 gives us 2 times 180 divided by 4 equals 360 degrees divided by 4 equals the 90 degrees that we expected. Then for a pentagon, make sure we get the same thing we had gotten before. We notice that for our pentagon, we're going to get 5 minus 3. So now we've got n equals 5. So we've got 5 minus 3 times 180 divided by 5 equals 2. 5 minus 2, which will equal 3. So we get 3 times 180 degrees divided by 5. Unsurprisingly, gives us 540 degrees divided by 5, which is going to give us the same 108 degrees we had gotten before. So if we look at a hexagon, n equals 6, we notice that we're going to have 6 minus 2 times 180 all divided by 6 equals 4 times 180 all divided by 6. And so we get 720 degrees divided by 6 gives us 120 degrees. So what can we do with that? We notice that if we're looking at, for a given n-gon, we're often interested in perimeter and area. And so, for a regular n-gon, with side length d, we know the perimeter, is n times d, because there are n sides, they're all of length d, quick and easy. So, for example, a regular octagon with side length (4 centimeters) has perimeter of 8 times 4 centimeters, which equals 32 centimeters. Nice and neat. Now, area tends to be trickier. We notice that if we want to get the area of a regular n-gon, if it's not regular, we need to take lots more measurements. But for regular n-gons, all we need to know is the side length and those interior angles. To calculate area, we look at, again, breaking the polygon into triangles. We notice that for an inside polygon, the interior angles must be n minus 2 times 180 all divided by n, and that tells us that the subtriangles that we can create have an angle of 360 divided by n, and two angles of measure n minus 2 times 180 divided by 2n. So this all sounds very complicated. In actual practice, it's a little bit more straightforward. If we look at a hexagon, regular hexagon, with side length of, side length of, let's make it 12 centimeters. We notice that we can break up one of those subtriangles. We'd already seen that the central angle has to be 60, and we actually notice that we're going to see that those other two angles are also 60. Because we had seen these interior angles were all 120s, and so the triangle ends up having half that, gets us 60. So this is convenient because it has a base of 12 centimeters, so we can just use a little bit of trigonometry. We notice that we can break that in half. We notice that the height of that triangle, must satisfy tangent of 60. Tangent of 60 degrees equals h divided by 6 centimeters, because we notice we're looking at half of the triangle to deal with the height. We know we've got that 60-degree angle, and we've got the base is 6 centimeters. And so tangent of 60 is h divided by 6 centimeters. And so tangent of 60, we know that's going to wind up being radical 3. So we've got square root of 3 equals h divided by 6 centimeters. And so that tells us that the height of the triangle has to be 6 radical 3 centimeters. So now we know that the area of the triangle has to be 1/2 base times height. So we're going to get 1/2 times the base is 12 centimeters times the height is 6 radical 3 centimeters. And so we end up getting 36 radical 3 square centimeters. So now that we've got that, we know that the area of the whole hexagon is going to end up being 6 times the area of the triangle and so we end up getting 6 times 36 is 180 plus 36 is 216 radical 3. 216 radical 3. Square centimeters. And then if we have a calculator, we can approximate that. We know that's going to be 216 times approximately 1.76. And quite often we're going to be interested in getting those approximations. We're very rarely going to see a need for 216 radical 3 square centimeters of carpeting. And so we can find out the square root of 3 is 1.73. And then we're going to get that times 216. And that gives us approximately 374 square centimeters. So we can theoretically create a formula for this. We're probably not going to, although you might see a homework exercise on that.